So we're going to do one last example in this sequence. We've been looking at approximation algorithms. We've been looking at guess and check, exhaustive enumeration. We saw when we wanted to move to floating point, we needed to be a little more clever, and that led us to the idea of bisection as a smart way of reducing the computation at each stage, especially when we have functions or problems where there's a monotonic relationship between the value we're looking for and the guesses we're making. There's one other very powerful algorithm for doing approximations due to Sir Isaac Newton, often called the Newton-Raphson algorithm because it was found at the same time by Newton and by Raphson. Here's the basic idea behind it. We want to find the root of a polynomial. And I'll remind you, a polynomial p of x is some sequence of coefficients and powers. So it's a sub n times x to the nth power plus a minus sub n minus 1 times x to the n minus first power and so on. It's just a sequence of numbers times powers of x. And what we often want to do is find a value r such that p of r is equal to 0. We want to find the root, the place where on that x-axis that graph crosses 0. Now, it sounds like a lot of math. Let's make it a little simpler. A simple way to think about this is if we wanted to find, for example, the square root of 24, we just need to find the root of the polynomial x squared minus 24. Makes sense. If we combine the value of x such that x squared minus 24 is equal to 0, we're done, because that's the thing we want. Now, what Newton showed was that for things like polynomials, if g is an approximation to the root, to the place where it's equal to 0, then g minus the polynomial evaluated at g divided by p prime evaluated at g is a better approximation, where p prime is just the derivative of p. And if you haven't done calculus, don't worry about it. We'll show you in a second what that means. But this is a powerful tool. Newton proved this, that given an approximation, g minus p of g divided by p prime of g is a much better approximation. Okay, so what does this have to do with things? Well, let's look at an example, a really simple case. Suppose our polynomial is just some coefficient c times x squared plus k. Then its first derivative is just 2cx. And in particular, if the polynomial is just something simple like x squared plus k, then the derivative is just 2x. Why is that nice? Well, Newton-Raphson says that given a guess g for the root, a better guess is just shown right here. It's g squared minus k all divided by 2g. And remember, we were using this form to find square roots, because it says if k is the value whose square root I want to find, then that's the polynomial I want to use. So this little formula says here's a better way of finding a guess for the square root of k. All right, let's put that together. We can now have another way of generating guesses, which we can check, which turns out to be very efficient. So here's some code that would do it. Again, I've got a little epsilon that tells me how close I want to get. Let's assume I'm looking for the square root of 24. We'll try some other examples in a second. I'm going to give an initial guess, which will just be y divided by 2. It's not a very good guess, but it's a reasonable place to go. And look at the code. Very crisp, very clean, very efficient. It basically says, check to see, am I close enough? Is the difference between the guess squared and y less than or equal to epsilon? If it's bigger than that, I'm not close enough. And then Newton says, get a new guess by taking the old value of guess, taking guess squared minus y, divide it by 2 guess, which is the derivative, and use that to create a new binding for guess. Just keep updating. Do that until I get close enough, and when I'm done, just print out the result. Nice and crisp. What's this doing? It's generating guesses. There's the generation. But it's not doing it exhaustively. It's using this property of mathematics to get it. And then it's testing right here to see if I'm done. So it's another example of a generate and test kind of algorithm. And let's look at what happens if we run it. So in my idle, I've got just a version of that. I'm going to do it with 24 to start with. And if I evaluate this, it prints out its guesses. Starts with a value of 14 and then goes to 7, 5. And you see, in just 4 guesses, it gets a pretty good answer. Let's try a different example. Let's try our good old example of 25. Again, if I evaluate that one, you see again, in basically 5 steps, because the first one was using 12.5, it gets to a quite good approximation of it. Let's try something even bigger. I'll go back over here. Let's do my example of 1, 2, 3, 4, 5. And let's evaluate that. And if we do that, what did it take me? 1, 2, 3, 4, 5, 6, 7, 8, 9. In 10 steps, it got to a really good solution. So this is what? This is another way of simply figuring out how to generate good guesses and then testing them. So, we've now seen several examples. We've got this idea of iterative algorithms. We're using the same piece of code over and over again. We're using that to build up this idea of a guess and check method, where we guess solutions and then check them. We use a looping construct to generate the guesses, and then we just check and keep going. And what have we seen? We've seen we could do exhaustive enumeration, where we just do a whole bunch of trials. We could cut down on the search in a clever way by simply using bisection, bisecting the range of places where we're looking for guesses until we get to something close enough. Or for the root finding case, which turns out to be a very general case, we can be really efficient by taking advantage of a mathematical property to very quickly cut down on where the solution lies. Those are examples of iterative algorithms, and they're examples in particular of guess and check methods that turn out to be really powerful, and we're going to give you a chance to explore those as we move through the course.